Hello, good morning, students. On last lecture, we learn about the different types of the process, which depends how they can be changed. The first law of thermodynamics. Now let's start the enthalpy. Enthalpy, which is denoted by the symbol capital H, it is a system, or we can say that it is defined as the sum of internal energy of the system and energy that arise due to its pressure and volume. So this internal energy, it is a bunch of the energy. On last lecture we learned what is the internal energy, and hence the enthalpy, which says that H is equal to U plus PV. Now what is U? U is the internal energy of the system, and PV, which is the energy required for the pressure volume work. So mathematical expression is that the enthalpy is defined by the equation H is equal to U plus PV. Now internal energy is also state function, pressure volume also showing the state function, and hence we say that the enthalpy is also state function, because U, that is the internal energy, P pressure, and volume, V are state functions. So of course H is also a state function. Obviously change in the enthalpy, that is delta H, is also depend on initial and final state of the system, and hence it is given by the equation delta H is equal to H2 minus H1, where H1 is the enthalpy of system and for the initial state, and H2 is the enthalpy of a system for the final state. So according to this equation we can write the H1 is equal to now U1 plus P1 V1. Similarly H2 is equal to what? U2 plus P2 V2. Now dear students, we have to substitute this value only in the above formula. So put the value delta H is equal to H2. What is the value of H2? U2 plus P2 V2. Substitute there. Subtract U1 plus P1 V1. Take the common term outside, U2 minus U1 plus P2 V2 minus P1 V1. Now U2 minus U1 final to initial, it's showing delta U. That is the change in the internal energy. So we write there delta U plus P2 V2 minus P1 V1. Yes, we learned that it is the total change in the pressure volume. So we write there delta PV. But for constant pressure, P1 is equal to P2 is equal to P. We already learned that concept, and hence we write there delta H is equal to delta U plus P delta V. If the pressure inside and outside is the same, or we can say that P external is equal to P, then we substitute the value of their delta H. In place of that, QP is equal to delta U plus P delta V. Now pressure is the constant, so that terms we showing as the isobaric process. So QP is equal to delta U plus P delta V. So this equation follows that delta H is equal to QP. Thus, an increase in the enthalpy of a system is equal to the heat absorbed by it when a reaction is run at constant pressure. Because we learned that the total process is the isobaric process, and hence pressure should be the constant. Since H is a state function, so of course QP is also the state function, although Q is not a state function of QP, and QV are the state function because the path of the process is defined. Therefore they can have only specific values. Therefore delta H is equal to QP. Thus the change in the enthalpy of a system is equal to heat transfer from it at constant temperature. The heat should be the absorbed. Actually the heat get absorbed by it when a reaction is run at the constant pressure. Relationship between delta H and delta U for chemical reaction. Now we just learned that the delta H is equal to delta U plus P delta V, and according to that we can find the relation in between of the delta H and delta U, means enthalpy and internal energy. For the reaction involving solid and liquid, delta V is usually very small because solid and liquid do not expand or contract significantly as the pressure change, because solid don't have this property. For such reaction we neglect P delta V, so what we get? Delta H is equal to delta U. But for the reaction involving gases, delta V cannot be neglected. This equation it says that delta H is equal to delta U plus P delta V. Delta U, we have to put the value there. delta H is equal to delta U plus P delta V. Therefore delta, there they given the mistake there, delta U plus P V2 minus V1. Therefore delta H is equal to delta U plus P V2 minus P V1, where V1 is the volume of gas and V2 is the for the gaseous product. So according to that, where the V1 is the volume of gas phase of the reactant and V2 is the gas phase for the product. If we say that the reactant and product gases are ideal, we can apply the ideal gas equation. Yes, right, that equation is which one? PV is equal to nRT. Suppose that N1 is the number of moles of the gaseous reactant which produces N2 mole of gaseous product. Then we write there PV1 is equal to N1RT and PV2 is equal to N2RT. The next step is the very simple. We have to substitute the value in the above equation. We get, so delta H is equal to delta U plus P delta V. In that formula we substitute the value delta H is equal to delta U plus N2RT. Now this N2 is came from PV1, PV2 and PV1 value we just substitute according to ideal gas equation. Now write the equation, delta U is equal to N2RT minus N1RT. Delta U is equal to, take the common term, N2 minus N1. Now the remaining term is what? Constant RT. So N2 minus N1 means what? Yes, delta N. This delta N value we have to write there, delta U is equal delta U plus delta N RT. Now we write at the substrate there is a G. G is for the gaseous product, and hence where delta Ng is the difference between number of moles of the product and those of the reactant. In the part first, we learn what is the work done and how it can be activated. So in the term 4.8.2, work done in a chemical reaction. So what is the work done? We already learned. By a system at constant temperature and pressure, it given by the equation W is equal to P external delta V. So if assuming that P external is equal to P, so what we get? W is equal to minus P delta V. Now what is delta V? You well known. It is the difference in between final to the initial. So substitute there, minus P into V2 minus V1. Yes, just multiply by the P. What we get? Minus PV2 plus PV1. Now in that we introduce the equation into the above equation. So what we get? W is equal to minus N2RT plus N1RT. Now what is that N2RT and N1RT? According to ideal gas equation, we get the PV1 is equal to N1RT, because general formula is PV is equal to NRT. We use there two terms, two different volumes, that is V2 and V1. So we write there conveniently PV1 is equal to N1RT, PV2 is equal to N2RT. So substitute in the above formula once again. We get W is equal to minus N2RT plus N1RT. Now take the common term RT outside. So what we get? Minus N2 minus N1RT. So N2 minus N1 means, yes, delta N, just we saw. So what we write? Minus delta N. Again at the base we write there G RT. That G is indicate for the gaseous term. The equation which gives the work done by a system in a chemical reaction. So the sign convention is the most important. So W is depends on the delta V. If in the there are the different cases, if we say that this term N2 is greater than N1, what we say that delta Ng is the positive and W is less than 0, or work is done by the system. If now the value of N1 is the mover, so what we say, delta Ng is the negative, value of W is get increased, and of course work is done on the system. Don't confuse in the on the system and by the system term. If we say that the value of N1 and N2, number of moles of volumes same, N1 and N2 is equal to same value, so what we get? Delta N is equal to, of course, 0. If delta N is equal to 0, then W is also showing the 0, and hence we say that if there is a no PV work is done when number of moles of the reactant and products are equal. So this term should be remembered, that in that equation we get delta H is equal to delta U. It is one thing is important to note, that work term has a significant value only when the number of moles of the gaseous reactants are differ from those of the gaseous product, and volume of the system is vary. So these things should be remembered, that the reaction is carried out in closed vessel or in the open vessel. This term is also indirectly affect on the rate of the reaction. So then if there is a PV work is no work is done, so number of moles of the reactant and product are equal, that is N1 is equal to N2, but W is equal to 0. Now the next and most important term, enthalpy of physical transformation. Transformation means to change, in which we first learned that the enthalpy of phase transition. Now what happened in the phase transition? Yes, one phase of the substance is converted into the another, but it required the condition that at constant temperature and pressure without the change in the chemical composition. We have to make a chemical composition should be the constant, but the phase should be the transfer. Then what will happen actual? For that we learn the first that the enthalpy of fusion. But in the enthalpy of phase transition, the enthalpy changes are accompanied with the phase transition process, such as fusion, that is the melting of solid, vaporization, sublimation. These are some different terms. So in which we first learn the enthalpy of fusion, which is denoted by the symbol delta fuse H. Now what is the fusion? Fusion means conversion of solid into the liquid, but it is not only the definition, so we have to learn the proper definition. The enthalpy change that accompanies the fusion of 1 mole of a solid without change in temperature at constant pressure is called the enthalpy of fusion, that is conversion of 1 mole of solid into the liquid without change in the temperature at constant pressure. One thing should be remembered, that we do not have to change its chemical composition also. Now the reaction is looking there, H2O solid into H2O liquid, so solid to liquid conversion. So delta fusion, that is there is a change, so it's showing that the plus 6.01 kilojoule per mole at 0 degree centigrade. Now why we say here 0 degree centigrade? Because state is get convert. Okay, so when 1 mole of solid ice it start to melt, the equation is indicate when 1 mole of ice is start to melt 0 degree centigrade at 1 atmospheric pressure. So of course there is a change in the enthalpy. Each 6.01 kilojoule or 6.01 kilojoule of heat is get absorbed. Is it clear? So amount of the heat get absorbed there, and hence the reverse of the fusion. When we say for the reverse reaction, the solid to liquid and liquid to solid, it is the reversible reaction. So reverse of the fusion is freezing of the liquid. Is it clear? The freezing of liquid is accompanied with the evolution of heat. First thing is that there is absorption, at the reverse reaction there is a evolution of heat. Thus when 1 mole of liquid water is freezes at 0 degree centigrade at 1 atmospheric pressure, so enthalpy change should be showing the negative symbol. So there is a change in the symbol also. Here it's showing the positive, now here it's showing the negative. Why this change is occurred? Because solid to liquid, remember solid to liquid, and there is a heat absorbed, so we write there positive. Now here heat get evolved from liquid to solid, and hence it's showing the symbol also the -1. So this enthalpy change minus 6.01 kilojoule, that is 6.01 kilojoule heat now released. Therefore the reaction is showing that H2O liquid which convert to H2O solid, delta freeze, that is the change in the enthalpy, is equal to minus 6.01 kilojoule per mole at 0 degree centigrade. Thus when 1 mole of liquid water freezes at 0 degree centigrade, heat should be the evolved.